So today we'll start the topic with the Doppler effect. The last session we discussed about the polarization, and today we'll do the Doppler effect, the formation of the interference, and the formation of the standing waves. First, how we define the term Doppler effect? Actually, Doppler effect is a relative change in the frequency or the wavelength when the source and observers are moving towards each other or away from each other. Let's take a simple example. Say we have a source which is says S is representing a source is there. It's a source of wave, it can be a sound wave, it can be a light wave, any wave. So S is representing the source of the wave. And we have observer one on the right hand side of the source and observer two on the left hand side of the source. So two observers are there. Those who just joined now the session, we started the topic Doppler's effect. So what is the concept of the Doppler effect? The Doppler effect is actually it's a relative change in the frequency when the source and observers are moving relative to each other. So example, we have a source and we have two observer one and observer two. And the source is producing a frequency, say 100 hertz. So when a source is producing a frequency 100 hertz and the source is stationary or at rest, so what is the frequency or number of waves received by observer one? Like, because frequency means how many vibrations in 1 second. So 100 hertz means 100 waves per second. So what is the observer one will receive? The observer one will receive 100 waves per second. And what about observer two? Observer two will also receive 100 waves per second when the source is stationary. So both will receive the same number of the waves per second. But now what is a Doppler effect? Doppler effect is a relative change in the frequency when the source or the observers are moving towards or away from each other. This is not a Doppler effect. This is like a source produce 100 waves per second. The two observers, which are also stationary and the source is also stationary, the source will receive, the observer one and observer two receive the same number of waves every second. But what if the source is producing 100 hertz and it start to move towards the observer one and away from observer two? Now what will happen due to the relative motion of the source as the source is approaching or moving towards the stationary observer? So as a result, what will happen? The number of the waves which are received by observer one per second will increase. So if the source is producing like 100 hertz, but the observer one will receive 120 hertz, more than what is produced. And it is apparent. The source radiations are not changed, but what is received by the observer will be changed because of the relative motion of the source. And as a result, what opposite will happen as the source is moving away from the observer 2. So the number of the waves per second will decrease for observer 2, and observer 2 might receive 80 waves per second or frequency of 80 hertz. So this effect, the relative change in the frequency when the source is moving towards or away from observer, what we call this, we call that as a Doppler effect. So due to the change in the frequency, the apparent frequency, it's not like the source frequency change, it is what is received has changed, and we call it simply as a Doppler effect. So when the source is moving towards the observer or observer is moving towards the source, what will happen to the frequency? The apparent frequency will be higher. And if the source is moving away from the observer, what will happen? The apparent frequency will be lower. But when we compare the wavelength is the distance between the two successive crests. So as a result, what will happen? The wavelength, as the source is moving towards the observer, the wavelength will decrease. And if it is moving away from the observer, the wavelength will increase. So the speed at which the wave travel does not change. We have the formula V is equals to F lambda. If the frequency is increasing, the wavelength is decreasing. This is happened when the source is moving towards the observer. And we have the formula V equals F lambda. If it moves away from the observer, the frequency will be shorter and the wavelength will be longer, the upper end. But the speed of the wave does not change. So this effect, the relative change of the frequency or the wavelength due to the motion of the source or observer. It's not like only the source, the movement of the source will cause this. Even the observer is moving, that will also call the apparent change, and we call that as a Doppler's effect. Is it clear, the basic idea of the Doppler's effect?
Yes.
Anyone having a doubt or a question in this? So Doppler effect, the definition of a Doppler effect, it's an apparent. No, the wavelength does not remain the same. Wavelength also changes. Speed remains the same. The speed at which the wave is traveling, that remains same. So if a source is moving towards the observer, the frequency will be higher, but the wavelength will be shorter. Speed at which the wave travel, that is not changing, because in a medium, the speed of the wave remain unchanged. So example, you have a source is there, S is a source. Here is an observer 1 and here is observer 2. So example, the source produce a wave. So this is the first wave which will travel. And the source is moving towards the observer 1. Now this is a new position of the source. When it produces a new wave, so the wave will be the center of the wave. Like it will produce a wave front, so that will be the wave front. With reference to this will be the center. Then the source further moved. Source has further moved towards the observer 1 and produce another wave. So when it produces another wave, this will be another wave. So what you will observe, you'll observe the distance between the two successive wavefront is called the wavelength. So if you compare the first wavelength which was produced and the second wavelength, the apparent, it's not like actually it's producing the same wavelength, but because of the relative motion, the wavelength has changed. So when the source is moving towards the observer 1, the wavelength which observer 1 will receive, that will decrease and it will receive more waves in word second. Where opposite will happen for observer 2, the opposite will happen for the second observer. So the wavelength will be longer and the speed will be, the frequency will be lower. So this effect, the relative change in the frequency and the wavelength due to the motion of the source and observer, we call that as a Doppler's effect. Is it clear? The concept of the Doppler's effect?
Yes.
Anyone having a doubt or a question in this? Now, what is the application of the Doppler's effect? The definition of the Doppler effect, the apparent change in the frequency, this is a definition. The apparent change in the frequency due to the motion of the source or the observer is known as the Doppler's effect. How you will know how much the frequency or the wavelength will change? There's a formula for the Doppler's effect. As you can see here, as a source move away, the number of the frequencies which are received or number of waves which are received, that will be lower and the wavelength will be higher. If it moves towards, the wavelength will decrease and the frequency will increase. Now, this is a formula for the Doppler's effect. Why it's written plus minus? And how to know when you will use a positive sign and when you will use a negative sign. What is F naught? F naught is an observed frequency, like what we receive. It's not like the source, where Fs is a source frequency. Like what is a frequency produces by the source. V is a speed of the wave. We also represent the speed of the wave. But what about V naught and Vs? V naught is representing speed of the observer. F naught is a frequency, observed frequency. The frequency which we receive, we call observed frequency. Vs is a speed of the source. Fs is a frequency of the source. F naught is the observed frequency, the frequency which we will observe. So what will happen? Depending on the question, like example, if I say, even though human moves around the world and are present in different places of the earth, every human still receives the wavelength of a star as showing a frequency did not change, even though received. No, the apparent frequency we receive from the stars has changed. I'll come to the formula first. I'll give more examples about the Doppler effect. I'll come back to the formula. The the Doppler effect, because of the Doppler effect, we can represent, like we can find whether the object is moving towards or away and what speed the object is moving. The example, the Doppler speedo cameras are there, or the cameras which are used to record the motion of the car, like the speed at which the car is moving or it is over speeding. So what it does, it also uses the same concept that, for example, even the radar, radio detection and ranging. So say an airplane is there which is approaching. A radar send the waves. So example, it is sending the wave because, and the same thing, this is also sending the waves through the radar, both waves, but radar is using like radio detection and ranging. So radar is actually sending the pulse and receiving them back and finding how much it has changed. For example, it has sent the frequency or a pulse of 200 hertz. But when it bounced back at a higher frequency, like the frequency at which it bounced back might be 250 hertz. So the frequency which was sent was 200 hertz, but the frequency which is received is 250 hertz. So it means we receive a higher frequency than what was sent. So if we receive a higher frequency or the frequency appear to have increased, what does it mean? It means this object is moving towards the observer. Why did it increase? Because the number of the, as the object is moving, it is reflecting more waves per second. So whenever object move towards the observer, the same concept is, this is a Doppler effect. So what happened in a Doppler effect? That if an object is moving towards the frequency, the apparent frequency, the frequency which was sent and the frequency received will be different. If the object and the observer are moving, like observer and the source are moving towards each other, the frequency will be higher. If they are moving away from each other, the frequency will be lower. So same thing happened. What is sent was 200 hertz. But because this object is reflecting more waves per second as it is approaching towards the source, as a result, what will happen? The higher frequency will be there. And opposite will happen if this is, and opposite will happen if an object is moving away and the radar is sending the pulse. So it is sending 200 hertz. But what is reflected will be a lower frequency, like it might be 150 hertz. So if the frequency which is reflected from the object appear to have decreased what is sent, so what this give an indication? This give an indication that this object is moving away. So the motion, the relative motion of an object, the source and the observer cause a change in the frequency or the change in the wavelength. That is known as the Doppler effect. If we find that the frequency which is bounced back or the frequency which is sent by the source has changed, it has decreased, it means it is moving away. But if the frequency has increased, it is moving towards. Is it clear? The speed cameras were working. The same principle, it works. Same thing like the speed cameras, how it identify that the car is over speeding. So this is representing the camera and the car is approaching. It can work in both ways. If the car is like it can be placed other way around. Now what will happen? It send the pulse and the pulse bounce back. If the car was stationary, say it is sending 200 hertz. If the car is stationary, the same number of the waves will return back. But if the car is moving towards, so it will be, because it's moving towards, so what is received will be higher. So might be 220 hertz. So using this, it identify that this car is moving towards the source. So if the car is approaching or moving towards, then the frequency received will be higher than the frequency which is sent. Now, how much the frequency change, that decide the speed of an object. If there is a greater change in the frequency, it means the object is moving at a higher speed. If there is a smaller change in the frequency, that means the speed is lower. So using this, it can be identified like what speed the car is moving, because there's a formula for finding the speed of the objects as well. Like we just discussed, that frequency of the observed frequency is equals to speed of the wave, speed of object, speed of the wave, speed of the source multiplied by the source frequency. This is the formula which we use for the Doppler's effect. So what is V is representing? V is representing the speed of the wave. The speed, the wave which we use, that is represented by V. What V naught is representing? V naught is representing the speed of the object. What Vs is representing? Vs is representing the speed of the source. If the source is stationary, then Vs will be 0. If observer is stationary, then V naught or V0, it will also be 0. Fs is a source of the frequency and F naught is a observed frequency. So this will be Fs, the source frequency, and this will be F naught, the observed frequency. So if the source is stationary, this will be 0. We are using a radio wave, so we know the speed of the radio waves, the all electromagnetic waves, that is 3 exponent 8 meter per second. So if this is stationary, we know V naught, like V has, V is there, Fs is there, F naught is there, so we can work out what speed this object is moving. And using this speed, we can identify whether the object is overspeeding or it is within the limit. Is it clear? Same idea about, yes, Shahid, I will explain the use of the formula. Like when to use, I will come back to the formula. I was just giving an example. I will come back to the formula in detail. I will discuss that. Right now, just application and then I will jump to the formula. What is a redshift? Redshift and the blue shift, like how we can say that the universe is expanding. The same concept. Look, as we know, different elements have a unique spectrum. Like every element is having a unique spectrum, give a specific amount of waves per second. That is known as a line spectrum, and this is used to identify the element as well. So every element is like the fingerprint of the element is a spectrum which this element gives. So, which is also known as a line spectrum. Now, for example, if you are observing a galaxy or a star, or and another element like hydrogen, because most of these stars contain hydrogen and helium, so we are observing the hydrogen in the lab. And we work out that in the lab, the hydrogen, every element is having a unique spectrum. Like unique spectrum, when I say, it means it gives a certain amount of the waves, certain amount of the wavelength. So that is called a line spectrum. So example, say the line spectrum of a hydrogen is say 200 nanometer. This is just an example. In the lab, the wavelength at which the hydrogen is giving us radiation, it's 200 nanometer. And we are observing a hydrogen in a galaxy, and we observe that it is also emitting out radiation. But the radiation which we receive on the earth, it's not 200, it's about 220 nanometers. So what this give an indication? This give an indication that what we receive is longer than what was expected. We expect, because this galaxy also contain hydrogen. So if it contain hydrogen, it should give the same wavelength as hydrogen in the lab. But when we observe the wavelength we receive because of the hydrogen, it's a longer wavelength. So if it is a longer wavelength, what this give an idea? This give an idea that this galaxy or this group of stars are moving away from us because the wavelength has increased. The observed wavelength, the wavelength which we observe, nanometer is a unit of wavelength. So it can be wavelength, it can be frequency. So the wavelength which we receive is longer than what we expect. So what we call that as a redshift. Why we call redshift? Because we have violet, indigo, blue, green, yellow, orange, and red. Red is having the longest wavelength and violet is having the shortest wavelength. So when we receive the wavelength from this nearby galaxy or the star, it appear to be on the longer side. So what we call it appear to be a longer side. So we call that as a redshift. So most of the galaxies around us are giving us a redshift. So that also that's why we conclude that the universe is expanding, because most of the things around us are giving us redshift. But it's not like all of them are giving redshift. There are galaxies which are giving us another shift, which we call a blue shift. So example, we are observing a hydrogen on another galaxy or the star, and we found that the wavelength which we receive, it is 180 nanometer. So expected, because of the hydrogen in the lab, expected is 200, but the wavelength is shorter than what we expect. So what this give an indication? This give an indication that this object is moving towards us. So if an object is moving towards us, what we call that as a blue shift. So in a redshift, what will happen? The wavelength will increase and the frequency will decrease. In a blue shift, the wavelength will decrease and the frequency will increase. So, and if a red shift is there, it means it is moving away. And if it's a blue shift, it means it is moving towards. So due to relative motion, the frequency or the wavelength which we receive will be different from the frequency which is produced. We call that as a Doppler's effect. And Doppler's effect is having many applications. Like using this Doppler effect, we can identify that whether object is moving towards or away from us, as well as the speed at which the object is approaching. Is it clear? The concept? Now, what about the formula of the Doppler's effect? Yes, speed of the wave is constant. Speed of the wave does not change. So the formula for the Doppler's effect, this is the formula for the Doppler's effect. What is F naught? F naught is a observed frequency, like receive frequency. What is V? V is the speed of the wave. If we are using a sound wave, light waves, that's the speed of the wave in that medium. What is V naught? V naught is the speed of the observer. What is Vs? Vs is the speed of the source. And what is Fs? Fs is the source frequency. But how you will know? As you can see, it is written plus minus here and it is written also minus plus. So how you will know what you will use, like which sign, whether you will add up or subtract? So you have to use, you can memorize this, but you can also use a concept that if we have Usually in A levels, like AS, they keep the observer constant most of the question. Like the source is moving, usually observer remain constant. For example, we have because different scenarios are there. Example, we have a source which is observer is stationary. Okay, observer 1 is stationary and observer 2 is also stationary. Both of them are at rest. This is also at rest. Usually in the question, as I mentioned, observers are stationary. They consider, but it can be moving as well. So both observers are stationary and the source is moving towards observer 1. The frequency of the source is called Fs, and the speed at which the source is moving, the speed of a source is called Vs. What about the stationary observer? The observer is not moving. So what is the speed of this observer? Zero. What about the speed of this observer? That is also zero. Now, the observed frequency is O here and observed frequency is F naught or FO, you can also say. Now, as we know that the source is moving towards the observer 1, so if a source is moving towards observer 1, the frequency which is received by observer 1 will be higher, where frequency received by observer 2 will be lower. So we have the formula that the observed frequency, this V naught is 0 because observer is 0, so this will be Vs divided by V. Now what I should do, it should be plus or minus. How I will know? Because the observed frequency is higher. So if the observed frequency is higher, it means the denominator should be smaller because of this observed frequency is higher. So means this denominator should be smaller. So how the denominator will be smaller? It means that in that case, I should use V minus Vs. Because when I do V minus Vs, the denominator will be smaller. So the F naught will become higher. So when the idea is that when the source is moving towards the observer, the formula will be V divided by V minus Vs into Fs. Is it clear, this formula? The observed frequency. So when the source is moving towards the stationary observer, because right now V is the speed of the wave, that does not change. The speed at which the wave travel, that does not change. That's why V will be constant. The frequency will change and the wavelength will also change. Same thing for the second observer. What will happen? The F naught is smaller. So if F naught is smaller and this is stationary observer, so V minus, because if F naught is smaller, so this denominator should be higher value. So in that case, it will be equals to V plus Vs. Means in the denominator, the speed of the source we will add as the observed frequency is smaller. So if the source is moving towards the observer, we will subtract the speed of the observer from the speed of wave. And if the source is moving away from the observer, we will add the speed of the wave and the speed of the source in the denominator. Is it clear? The first part of the formula, like when the observer is stationary. Any doubt in this? The first part? Because the apparent frequency will be higher, so the denominator should be smaller. Here, apparent frequency is lower, so the denominator should be higher. Our denominator should be higher, so we'll add the source frequency. Source frequency, we'll add the source speed. Source speed is always in a denominator, and the observer speed is always in a numerator. Then another scenario, the second scenario, if the source is stationary and the observer is moving, or observers are moving, like we have a source which is at rest, not moving, so the speed of the source is zero here. We have observer 1 which is approaching, moving towards, and we have observer 2 which is moving away. So it's moving towards and this is moving away. Now the source frequency is Fs, the observed frequency is F naught here and F naught. What will happen to observer 1 frequency? Will it be higher or lower if it is moving towards the source? Observer frequency. Will it be higher or lower? It is moving towards. So when the observer source are moving towards each other, the frequency will be higher. It will receive the frequency, the number of waves received per second will be higher as it is approaching. And it is moving away, the number of the waves per second will decrease. So here we have the formula F naught. The speed of the observer is V naught. Here the speed of observer is also V naught. So here we want a higher value of F naught. Because the source is not moving, so this factor is 0. So it will be Vs. Now what I should do, because I want to increase the F naught will increase. So in that case, how it can be increased if the numerator increases? So we'll add V plus V naught. And what about the observed frequency? It has to be decreased. So in that case, it will be V minus V naught into Fs. So opposite will happen. That's why you can see the signs here. It's written plus minus and here is minus plus. So what is the concept here? That if the observer is moving towards the source, we will add the frequency. But if the source is moving towards the observer, we will subtract the frequency of the speed of the source. So it is opposite. That's why it is important, rather than memorizing a formula, try to understand like what will happen to the frequency. So you can check whether it should be added or subtracted. If an observer is moving, you will add. If an observer is moving towards, you will add. If it's moving away, you will subtract. If a source is moving towards the observer, subtract. And if a source is moving away from the observer, add. Is it clear, the concept and the formula? And if we say, if we see a train is there which emits, just an example, let's say a train is there which emits a note which is having a frequency of 800 hertz. And it is approaching a stationary observer. So if it is approaching a stationary observer with a speed of 60 meters per second. So we have a train and the observer is there stationary at rest. And it is producing a sound, like the speed of a sound is there, speed of a sound in air, which is 330 meters per second. It is producing a sound waves. So what about the observer speed? It is 0. What about the source speed? The speed at which the source is moving, it is moving at a speed of 60 meters per second. What about the source frequency? The frequency is 800 hertz. We want to find the observed frequency, like what observer will receive. That's what we have to find. So we have the formula that the observed frequency, first thing, as the source is moving, towards the observer, what should happen to the frequency? Will it increase or decrease? So it will be higher. So if the frequency is higher, and remember, the observer speeds are always in the numerator and the source is in the denominator. So V is the speed of the wave divided by, because the observer is stationary, so we don't have, like it is plus minus 0, it does not make difference. So even if you don't write, that's fine. Then what should happen? Because the F naught should be higher, so the speed of the source should be subtracted. into the source frequency. So when we simplify the speed of the wave, which is 330, multiplied by frequency of the source, which is 800, divided by the speed of the wave 330 minus 60. So when we simplify, that will give us the observed frequency. What is the observed frequency? So 330 into 800 divided by 270, which is 980 hertz. So it means 980 hertz is the frequency which is received by the observer, the stationary observer. Yeah, rounded off to 980. It is about 978, 980, it's fine. So the observed frequency will be different. Can a movement be at an angle? Yes, it can be at an angle, but what we are considering a rectilinear motion, the straight line motion. If the movement is at certain angle, then we have to take those angle, but we are taking only a rectilinear motion in this case. Means we are all considering that the wave is traveling in a straight line, not making any angle. That's what we consider. So the apparent change in the frequency due to a relative motion of the source and observer, we call that as a Doppler's effect. Anyone having a doubt or a question in this Doppler's effect?